Okay, so we're recording, I guess. Yes. All right, so let's continue. So we did this kind of, what's it called? Spectral calculus. So I'm going to now draw some kind of a table, not a table, draw a kind of diagram for you that kind of has all the elements that these operations that we discussed in one picture. So it's good to have one picture that has all these different components of the theory that we developed. So the picture is going to look like, it's just one line, going to look like this. So we go from functions to vector fields. And from vector fields, we go to vector fields again. And from vector fields, we go back to functions. It kind of comes full circle in a way, but it's not the circle, it's line. But you can imagine it's like coming full circle back to where you start. So how did we go from functions to vector fields? What operation did we apply? Remember? If I have a scalar function or function, how did I produce a vector field? Yes.
Gradient?
It was gradient, exactly. So I write it in two notations that we use. First of all, the English notation is grad, and the math notation was nabla, inverted triangle. Right? So this was great. Good. From vector fields to vector fields, how did we go from vector fields to vector fields? What operation did we use? What operation? Can you tell me?
Is it curl?
It's curl, right, exactly. Absolutely, thank you. So this was curl, and the math notation for curl was this. It was a nabla and it was a cross right beside. And from vector fields to functions, how did we go from vector fields to functions?
Divergence.
It was divergence. That's the only thing that's left, right? that's a good guess. So this was divergence. I wrote it as dive or nabla dot. This was divergence. Okay. So this line contains all these operations that we did on vectors, on vector fields and scalar fields. There is a gradient, produces a vector field, and this produces a vector field, divergence produces function. And what did we discuss about these things? And we noticed that if we follow curl after gradient, we get 0. Remember? So there were some rules. One of them was that curl of gradient was equal to 0. Do you remember this equation that we proved like last lecture? So we can just write it as curl of gradient is equal to 0. So curl of gradient of f, for example. And divergence of curl, we also showed that it's equal to 0. That's what we did also. So the second line, or third line rather, was that we also proved that divergence of curl. So this we denoted as divergence of curl of, say, f So remember, this little f is a function, and this cap f is a vector. So this is a vector. I'm sorry. Okay. So these two rules are absolutely fundamental. These are supreme rules. They are very, very important. Very, very important. And we also said that under some nice conditions on the domain that we are working on, some topological conditions on the domain, the converse is also true. Namely, if you have a vector field whose curl is equal to 0, then this is going to be gradient of something. And converse holds. Converse. And conversely, if, first of all, the first condition is that curl of something, curl of, for example, some vector field f equal to 0, then f is equal to gradient of f. Under suitable conditions, though. I just say vaguely, but I told you what kind of conditions almost last lecture in under suitable conditions. Certainly you can be sure that this is true over R3, for example. If your vector field has no singularities and is defined over the whole space, then that's absolutely okay. You can do that. And the second one was that if divergence of some vector field B equal to 0, then B is equal to curl of A. Both of them is under suitable conditions. But the thing is, the suitable conditions are different in each case. That's the bad news. So you don't worry about the suitable condition, meaning on R3 everything works. There's no need to worry about it. All right, so that's the thing. And also we had some terminology, right? So these sort of vector fields that are gradient, what was the other names for these things? Gradient vector fields. What did we call them? If a vector field has is gradient of something, then that vector field was called conservative, right? Conservative. So gradient vector fields, so say f equal to gradient of f, is called conservative, and this little f is called the potential of that vector. F is called potential of a potential of f. So it had many names: conservative, gradient. There is another name for that, which is also called irrotational. So irrotational. So for now, let's not discuss that. I can discuss it later. So we have that. Now, vector fields that whose divergence is equal to 0 also have got their own names. I'm going to erase this part. Divergence of B equal to 0. This B, so if divergence of vector field is equal to 0, B is called, well, one obvious terminology is that we call it divergence free. Well, We can do it, and it's used. It's called divergence free. But then there is another name which is very suggestive. It's called incompressible or incompressible. Okay, so now we have we have to understand what does this mean? Why these are called incompressible? And what's the importance of this condition, and what's the importance of this condition? So that's what we want to do next. And if we do this, we do good justice to this program, then you have a kind of reasonably kind of initial understanding of vector fields. I always emphasize vector fields are difficult objects to understand. I mean, they are far more complicated than functions. A scalar field is easy. For example, temperature field, distribution of temperature in this room is easy to understand. From point to point, you just measure temperature and it changes. Near windows is colder, inside it's warmer, and then near the heat source even warmer. But it changes, you know, from point to point. But then try to imagine an electromagnetic field due to all these lights, your cell phones, and all these things that is kind of going around in this. It's very complicated. Hard to see what's going on, but there is some pattern, there is some logic to that, but it takes time to digest all that. And one way to understand these things now is to study integration of vector fields. So I put it like this: what can we do with vector fields? What can we do with vector fields? Well, we can integrate them. We can integrate them. That's a short answer, and I'll tell you how. So the full picture, full theory, it will be almost full, will be done next term. You learn these things next term, integration of vector. What I'm going to do is a sketch that I need in order to understand these terminologies and things for this part of the course. So full definitions next term. But it doesn't matter. The definitions are so intuitive, so natural, so useful that we can just grasp it if I tell you what we can do. Okay, one of the things that we can do with the vector field is a flux. So the flux of a vector field along the vector field through a surface. So what is a flux? So the flux is like this. So you have a surface, whatever you want, whatever shape. You know, we study surfaces after all, right? So we have different types of surfaces. So imagine you have a surface like this in your 3D space, and imagine you have some vector field. Things like that. So the flux of this vector field along this surface, this flux is equal to, so the notation first of all is that integral f dot d, say, sigma over the surface S. This is a notation. What do? You just look at the following thing. You just look at this point. There is some small area here, some small area here, some small area. So you chop your space into small pieces, right? You chop it into small pieces. And for each piece, you just take the normal vector like that, right? So you just take normal vector, and then normal vector. And this really means we are taking the dot product of f with this normal, unit normal vector times the area. Okay, so this is equal to integral of f dot basically n times dA. So this d sigma is n times dA. N is the unit normal vector, dA is the length of the vector that's proportional to the area that's concentrated on that point. So that's, and you just add, right? So you just add it. Okay, that's it. So that's the flux of, that's the flux of the vector. Okay, so that's what we call flux. And so what is the meaning of flux now? So the meaning of flux is like this. Imagine you have a river, for example, and you have put a surface inside your river flow, and imagine these are velocity vector fields of the river flow. Then what this measures is exactly the amount of water that's carried through the surface in unit time. That's it. If your vector field is vector field of velocity of, for example, river. So this basically means that amount of liquid flow, whatever, passing through. I mean, this is one interpretation, passing through surface. In unit time. I mean, for example, to convince yourself that there is some logic in this definition, you can do this. You can look at this hypothetical situation. So, what is the hypothetical situation? Imagine your vector field is actually tangent to surface at each point. Tangent to surface. How much flow? How much liquid passes through the surface in unit time? Nothing. Exactly. Nothing will pass because it's just tangent to the surface. Nothing will pass. It just stays inside or outside if you want. And the maximum amount happens if it's going orthogonally to the surface. That's what maximum is, right? You achieve the maximum. So you can sense that this is indeed just measures the amount of flow that passes through it. Okay, so that's the flux. You will study this next a little more formal way, but that's the best definition you can rely on. That's the best definition money can buy. All right, so the other things is the circulation. I just tell you the other operation we can do circulation. Oh, we have time, very good. So next is circulation. Of a vector field. Curve. So here is a curve. It's just a random curve in space. It doesn't matter what it is. It's just a curve, any curve. Actually, it doesn't have even to be closed. It could be whatever curve. But I'm just taking it closed. So you just go like that, and then you have a vector field. And we just look at this vector field along this surface. So we want to study the circulation of this vector field along this path, gamma. So circulation is equal to, again, is an integral. So there's this notation. So just to give you the impression of the circulation. So this is a new integration notation. So over this curve C, and we have F dot. So we just take the dot product with the tangent line to the curve this time. So with dl. So this dl is like this. So the length of this dl is equal to infinitesimal length of the curve at that point, and is along this. This is along this tangent line, unit tangent vector of the circle. Unit tangent vector, of course, we discussed, right? So this circles. Again, to understand this, you can put yourself in a kind of hypothetical situation again, where imagine this is orthogonal to your curve, for example. If your vector field is orthogonal to your curve, then there is no circulation. It's zero, right? It doesn't move around this because this is zero. But if your vector field is tangent to the curve at each point, you're going to get maximum amount of circulation. So this really rotates. The vector field really has some net rotation around this. So this circulation also makes sense. Circulation makes sense also. This one. So this is our second operation. So this was the first one. So this was the second operation. There is a related to this. There is a third operation, which is yeah.
I was just wondering for flux, since you're integrating over area, wouldn't it be a double integral?
It is a double integral, right? I mean, definitely, but for me as a mathematician, there's only one integral sign. Because you go into three-dimensional, you go into five, then you go into infinite dimensional, and then you want to integrate over all kinds of animals and objects. So you integrate over like space of all paths and stuff like that. So it's better to use, for me, just one notation, but no. Double integral. Right. Yeah. Double integral. Yeah. I mean, next term you get this stuff. Okay, so this is the second operation. Now the final thing you can do, so what kind of other things you could do with vector fields, by the way? You remember from your physics courses? What other thing we did with vector fields?
Fluid dynamics?
Yeah, I mean, of course, if you know fluid dynamics, you are very well off. that's beautiful knowledge, of course. I wish I knew fluid dynamics very well. I'm trying to learn it though. But you can do in mechanics. You can compute work using integration of vector. The work also is done by integrating a vector field along a path, right?
We never. I remember doing work as an.
How did you do work? Yeah. How did you do work? How did you calculate work? It was an integral, right?
Yeah.
So what was it? Work is F dot ds.
Yeah.
Okay.
Yeah.
So
force over a distance.
Force times ds. But this is the same.
Yeah.
So this is also work. So I just write this is equal to work.
And we just never related it to.
Wait, to what?
We never related it to vector.
Oh, but the force that you have, of course, is vector. So this is work done. I mean, this is another interpretation I'm saying. This is work done by F in moving a mass. Well, I mean, I have to multiply maybe. No, I think moving a mass, maybe I have to multiply by M, I'm not sure. Moving a mass along C. So we can do that, right? Okay. So we have these three operations, three different interpretations of integration of vector field. Now, the beauty of these results is that we can say something about these operations actually. So there are theorems. For example, let's look at this one theorem. It's called Divergence Theorem. So this is again, you will study in detail, but I just rely on your intuition in this case and kind of common understanding. Divergence theorem. So the divergence theorem says the following thing. So it says the following. Imagine you have a vector field that's defined on some space, right? And we have some sort of kind of shape, which is a three-dimensional shape with a surface S. So there is a volume here, volume D surrounded by, surrounding, double R or one R, surround. 2R or 1R? Something tells me it should be 2R.
Yeah, 2.
Yeah.
I think so.
4?
No, I said yeah. Yeah, no, not 4.
There's no letter with 3, man.
Yeah,
2.
2, I think.
2 sounds right. Surrounding D. Surrounded, no, in between I forgot what I was going to formulate. Surrounded by, surface S. Because I already used D, so I have to use it, you know. Surrounded by surface S. Okay, so we have two things to play with. There is this domain D and there is this surface S. And F is a vector field. And F is a vector. Okay, so then the theorem says that integral of divergence of F over, so because to make you happy, I just put triple integral this time. it's a triple integral over D. Okay. I would write 1, but that's okay. It's equal to double integral. Okay, this is very glorious now, kind of formula. You like it. Sigma.
Well, that's how we do it in physics.
I know. We have time to spend, we don't. Time to waste. So to say. Sigma, no, I love physics, of course. You know that. Double integral sigma, and then F dot D sigma. So what does this result say? It says that the flux of your vector field is equal to integral to divergence over the whole volume. So this is flux, right? Is equal to integral of the divergence. This is the total divergence. Total integral divergence. So, if I know that divergence of a vector field is 0, then what does it mean? It means that the flux is 0. Right? So that's what so this you will prove in next step, but that's okay. So because the way this the syllabus of this course is structured, I feel guilty if I give you those definitions about incompressible, irrotational, without giving the justification where these terms come from and physical intuitive meanings of this thing. So that's why I'm just relying on a little bit extra knowledge there. Okay, so anyhow, so the corollary of this divergence theorem, so this is the divergence theorem. The corollary is that if divergence of F, which is this, is equal to 0, then total flux through any surface is 0. Flux through any surface. I mean, closed surface, of course. It should be closed surface. Closed surface. Any closed surface. So this sort of flow or fluid has the property that everything comes in, has to go out. It cannot compress, it cannot expand. So this sort of flow is called incompressible. That makes sense. So divergence of F equal to 0. These vector fields are called incompressible vector fields. Well, you know what incompressible means. It means that you cannot shrink it and push it to just come through a surface and just, at least for some time, it stays there. Whatever comes from one side has to get out from the other side. So that's the idea of incompressibility. And it also means that there are no sources or sinks in this field. Because if there was a source somewhere, you know, it would absorb these things, and you could, I mean, the fluid could seep through from the boundary and just disappears at that sink. Or the fluid could be generated through one source, for example, then it would pour out the boundary. So this would be violated, and in that case it's not. So that's why this also implies that no sources or sinks in the fluid. No sources or sinks. Yeah.
Does that work in the converse as well? If flux is 0, then total integral divergence is 0?
Absolutely, Koyo. That's an excellent question, and that's true indeed. But you have to stipulate, you have to say that for any closed surface, no matter where, if this is 0, then divergence automatically has to be 0. Yeah. This is true because you can just write down this as limits of those small integrals, and then you use the theorem. It's easy to prove. Yeah.
Because I'm just thinking, if you take that surface, for example, and you put it within a uniform electric field,
yeah,
flux is 0 because all electric field lines that go and come out the other side.
Mm-hmm.
So for that uniform electric field, that vector field, that has a divergence of 0?
No, because if the theorem is true for all closed surfaces, you have to make sure that your result is true not just for one special type of closed surface.
Yeah.
If it is true for all closed surfaces, then the divergence is 0. That's for sure. That's absolutely true. But for all closed, for all sigma closed. Okay? Yeah. Very good. Excellent. So now I ask you a question. What is a natural example of a vector field that is incompressible? That's true, but magnetic field, where is it? You cannot sense it. Give me a real life example of a vector field that's incompressible.
That you can
tangibly, you can go and see it, feel it, and play with it. Yeah.
Water flow?
Exactly. Water is incompressible. Water is a very, very incompressible object. It's very hard to compress water. I don't know. If you have water in some say piston, for example, you want to press it, you want to compress it, I don't know how much energy you have to spend. A lot. It doesn't compress. So when you go just Thames River here, and look at that water flowing. Next time you're going over the Thames Bridge, for example, look down at the water and you see an incompressible flow vector field down there. It's a beautiful vector field because there are rocks and things there. There is some islands. They has to move around the island. There are some fish swimming and the vector field has to adjust itself around that fish body and everything. Just it's an amazingly difficult vector field, but nevertheless, it's incompressible. So you can say that divergence of that vector field is zero, no matter how complicated, how strange it might look like. So that's now give me an example of a vector field which is actually not incompressible.
An electric field?
That's absolutely true, yes. But then a more tangible, more down to earth, day-to-day example, maybe? Yeah, no, absolutely correct. The electric field is true, yeah. But something.
Wind?
Wind, exactly. Air. Air is compressible. It's very easy to compress. Just take a piston and then put air. I mean, this is I used to play with this all the time. I don't know why I liked it. I thought these things for needles and stuff like that. Just, well, I'm not using needles. Don't get wrong idea. I don't know why we had this at home, but don't get me wrong. But I used to press the knee. I just like playing with it, kind of this sort of thing. Just pressing it and then it goes up. So it's compressible, and this is the air. The air is really compressible, and but for some approximation, people use incompressible air assumption. But in general, it's very, very compressible. So this air. So yeah, divergence of the air molecules moving around, not air flow moving around, is not zero. So, and that's why you can have sometimes, yeah, okay, so more complicated situations. Okay, so now we understand incompressible very well, and compressible also very well. So that's one example. So now just to do a little bit of less maybe conceptual and kind of integration stuff, just down to earth example of this sort of dumb calculations. Let's do one of those maybe as an exercise, and then we get a better feeling. Then I write another equation which is related to curl. So, okay, so example, is the vector field F equal to R hat over R2? Remember what was this vector field R hat over R2? So this is what we derived last time. So this was like x2 plus y2 plus z2 to the power -3/2 times xi plus yj plus zk, right? So this is a vector field which is its length Okay, so now so I can just draw it like this, actually, if you want. You take concentric spheres, and so you draw this concentric spheres. This vector field is orthogonal to that, and its length is proportional to square of the distance. Otherwise, it's orthogonal to the surface, but its length is proportional to square of the distance. So, the inverse square of the distance, not the square of the distance, it's the inverse square. There is an inverse square law. So, for example, as you approach the origin, you get infinity, right? So there's a singularity at the origin. Okay, so anyhow, sorry, I drew it wrongly here. So it should decrease as you move away, it decreases. Okay, so. I wish I was more patient with drawing better graph, better things. I'm not patient, that's me. So, all right. So now, anyhow, the vector field equation is given here. Now I ask the question: is this incompressible or compressible? Is F compressible or incompressible. In other words, so what does this question mean? The question is, I'm asking, is it that divergence of f equal to 0 or not, right? That's what I'm asking. So is divergence of f, so i.e. is divergence of f equal to 0? Yeah, your answer is, you understand the question, so what would be your answer?
Compressible.
Is it compressible?
I would think.
Its divergence is 0? Okay.
Oh, sorry. Divergence is 0, so
You're saying it's not 0.
it's not 0.
You're saying divergence is not 0, so it's incompressible. It's compressible.
It's compressible.
Yes, compressible. You're saying this is compressible. Okay, so any other guess? From home audience. I give $5 to correct answer.
I feel like I got the wrong answer now.
The spectral field is divergence free. Yes. Yeah, that's what always surprises people when they see this. Divergence of the spectral field is 0. Answer. Divergence of f equal to 0, i.e. f is incompressible. You might be surprised, rightly so, because you might say, why you're surprised, by the way? Why we should be surprised? Because we think that there is there is something here that's just, there's a sink. We think that there's a sink here, right? Things are going there. So the idea of maybe no source, no sink is violated here, you might think. But this point is not in the domain of your function. This is out of the domain of the function. The result about the thing that we used, if you want to draw a surface and a domain D in this, you have to avoid this singularity. And then you just check that whether what comes in is the same as what comes out. Computer. For example, if you look at two concentric spheres here, and the total flux, what would be the total flux here, right? So the total flux here would be, here you have to use this sort of thing, and for here you have to use the opposite direction. They cancel each other. The total flux is 0, always. For at least this sort of concentric spheres, you know that, it's all 0. However, this is a very general statement. I'm claiming divergence of your vector field is 0. And this should be easy to check, right? That's not a problem to check that. So let's check it. So why divergence of this f is 0? So let's get our hands dirty and compute. So what is divergence of that? Well, this is equal to, so, you know, dA dx plus dB dy. You remember? Plus dC dz. Well, f is ABC, right? That was the formula for divergence. So what we have to do, we have just to take partial derivative of this guy with respect to x, and with respect to y, with respect to z, and then go c. So let's compute it. Instead of talking now, let's compute. Sometimes people say, shut up and compute. So. Okay, so let's compute. So ddx of the first part is x2 plus y2 plus z2 to the power -3/2 times x is equal to, well, there is this ddx of this term, so this is -3/2 times 2x times x2 plus y2 plus z2 to the power negative 5 over 2 times x, right? Plus x2 plus y2 plus z2 to the power, well, I mean, there's x. Right? I just used product rule. I didn't do anything else, just product rule. So that's good. So we just write it as this cancels negative 3x. I'm going to write it as, and this is x2, negative 3x2. Here is r to the power minus 5 over 2, right? And then plus r2. Right? So this is plus r2. Well, now partial derivative with respect to y, of course, is similar to this. dy of the second component, which is b, but just replace x by y, otherwise it's symmetric. Negative 3y2 r to the power minus 5 over 2 plus r2, and then ddz, and then ddz, c, just replace y by z this time, z, 3z2, r to the power minus 5 over 2, plus r2. And then add these things, right? So I have to add this with that and that. Add above three terms. So what you get? We get, there's negative 3 times x2 plus y2 plus z2. Times r to the power negative 5 over 2. Plus 3r2, right? Because r2 is common. We're just adding them. Plus 3r2. So what is that? That's equal to negative. Well, this is r squared. I mean, this one gives me what did I do wrong here? No, this is minus, so square 2 minus 5 over 2. Okay. So this is R2, yeah. So this is 2, 4 minus 5. I get negative. Did I do everything right here?
I think you're missing a sign or two, but that shouldn't make your calculations.
Which
incorrect.
sign of 2?
I mean, just up there, you forgot a negative in front of the 3. Oh, further up.
Oh, here?
Higher.
Oh,
Even
here.
higher. Yeah, negative 3z squared.
Oh, there's a negative.
Yeah.
There's a
And then-
negative.
And then under the ddx, you wrote negative 3 over 2, all that's correct.
Negative 2x, x2 plus y2 plus z2. This I have to subtract. First of all, I mean, is that correct? What I have here, is this correct?
I was going to ask how you got that x.
Well, the derivative of x squared is 2x.
Yes.
So this is 2x. But this negative 2 over 2, I'm not sure my vector field is correct actually. What is the vector field? Is this correct to write it like that? Well, what is r hat? R hat is unit vector, so that's equal to x2 plus y2 plus z2 to the power negative 2. Its length, which is negative half, x, y, z. That's correct. And then r2. So this is minus 2. So minus half, minus 2, 2 minus 1 minus 4. It should be minus 5 over 2.
You're missing a negative.
What negative?
When we derived r hat, it was negative xyz over square root of x squared plus y squared plus z squared.
Oh, here?
Yes, just right in front of that whole thing should be a negative. There should be a negative, I think.
No, there shouldn't be a negative. No, I mean, this is just a formula. But I mean, this is wrong, actually. This should be negative 5/2 here. This is negative 5/2. That's what I'm getting. If this is wrong, this is not negative 2, yeah.
You forgot an exponent on the second term when you took the partial derivative with respect to x.
Which
For,
one?
for the second term, it should be -3 up. It should be to the power of -3/2, shouldn't it?
Minus.
It is, but that doesn't change the rest of the calculation.
And then when you
Minus,
find
no, actually, it does. It does.
when,
Oh, this is -3/2.
when you substitute r in, shouldn't it be to the -5 as well, since x² plus y² plus z² is r²?
Yeah, that's r².
And then it would cancel out with the 5/2. It would cancel out with the 2, so you just get r to the -5.
I mean, at the end, I'm going to get 0.
Yeah.
But do you see that?
Yeah.
Okay, so I have to check this here because this is not, this doesn't sound quite correct to me because this part is here and then I have, so first of all, this has to change. This is -5/2. This is not correct. You see that? Look, I mean, the thing is r hat over r2, okay? No, R is, no, this is correct, this is correct. No, this is correct. R has a square root in it, and then R2 is just x2 plus y2 plus z2. So this is correct. Okay, so now what, so then comes to this, okay. So this is, okay, so this is R to the power -3/2. Okay, yeah, r to the power -3/2. Okay, so it's -3 r to the power -3/2 plus 3 r to the power -3/2. And this is yeah, so yeah, I mean, this is, it's easy to make this kind of silly mistakes. I mean, so we have to be careful. So now we have to kind of digest this result. Divergence is 0. The calculation shows divergence is 0, and we have some intuition about that, but we will do more. Now, another question I want to ask is this a conservative vector field or not? Is this conservative? That's a reasonable question. So there is some comment. I think it should be, yeah, that's right. That's correct, right? You have it. Now, another question is very important. Is this vector field conservative or not? Is F conservative? Sorry. Is it? Yeah, it's Friday. 125, 225. It's better be conservative. Is it conservative or not? So in other words, is there a potential for this vector field? We are asking if there's a function f whose gradient is this vector field. That's what we are asking. Someone talked about electric potential. Right? The reason you have electric potential, the reason you talk about potential in your batteries, and everything that you do using potential concept is because of this result. Because the answer to this question is yes, there is a potential. And that's the whole thing, right? So the answer is yes. Yes. And what is the potential then? F is equal to, it's just some constant, it doesn't matter, -1/r. or 1 over r in this case? Well, that the potential is inversely proportional to the distance. That's what you learn also in gravity and stuff. Potential of gravity is inversely proportional to distance, but the force of gravity is the square inversely proportional to the distance. Force is the same for electricity. So check this, and then on Monday we will continue. Yeah, so vector fields, again, are quite complicated object. Okay, guys, thank you. So I just stopped the recording now. Pause recording, yes.